So, hello everyone. Welcome to the second workshop of the event Comnet. We have Iega Jatin, who is one of the coordinators of the event, and he'll be starting the session today. So, Iega, you have this. So, Jatin, you have the stage.
Good evening, guys. Hope everyone are doing good. So let's start this workshop number 2. Uh, can someone confirm my screen and audio is good?
Yes, Bhaiya.
Yes.
Yeah. Thank you. So this workshop will be seeing some signal about signal space, Fourier transform, source coding, and some MATLAB hands-on. So let's recap some of the topics like important topics in the last workshop. We have seen this digital communication, how it happens. So I'll be revising this because you'll in this workshop we'll be discussing more about this in detail. So here what we have seen is we have some message or some from the source we have received some signal. So that signal we are sending it to the source encoding. So what happens there? The information is now that we have that signal is converted into some digital form, zeros and ones. So that signal, that information is now sent into channel encoding, where all that digital information is attached to some noise, useful noise, so that the information is not tampered. So that is sent into modulation, where the modulator sends out the signal into the channel. Through channel, it goes and some of the unwanted noises get attached, and in the when it received by the demodulator, the other unwanted noises cleared out. Then it is sent into channel decoding to check whether the information we have sent is proper or not. So the noise we have put, the needed noise we have put is cleared out. Then the data is now sent into source decoding, where the digital information is turned into information, the raw information we have got it from the sensor, and that is sent to the receiver. So this was the digital communication. So what is the signal space and stuff? So let me tell you, I'm speaking here and you're hearing something, right? So let's assume this is happening in a classroom or something. So I'm speaking and this is some speech. So whatever speech I'm giving you is a movement of air through over the time period of t. So this information or this waveform, what you observe, if you want to if you want to record over, like if you want to listen after a while, so you record this stuff. So you record some information. That recorded information is when you play it out through a speaker, the movement of air is repeated, like is regenerated, and that what you hear is the recorded version of my speech today. So let's this recording stuff, what happens inside and what is done of the continuous period of signals, what I spoke, what happens to that signal information is what we're going to discuss today. So the information I have given, there are lots of ways you can process it. So this is one of the way, like sampling is one of the way where you can break down the speech what I spoke. So what happens in the sampling is the speech or information is broken down in discrete points of time. So when you have a sinusoidal signal, this gray signal is the signal we have. So now at particular instance of time, I take out some values from the wave. So here I take out at particular intervals, and thus after that those points are the information I have. So later, when I want to when I want to hear it again, so from that information, I take out the graph, the signal graph, and I get it. So this is what happens in sampling. So sampling cannot be done however you want. You cannot break down into whatever time length you want. So there are some rules you need to follow. So Okay. So those rules are is known as Nyquist sampling theorem, where he tells about the sampling frequency should be greater than or equal to 2 times the highest frequency present in that signal. So why do you think this rule is kept? This rule was came into action because of the
Sir,
problem of aliasing. What is aliasing? See,
sir,
let me tell you. So the graph you see here, the signal. So the red signal is the initial signal we have. So at some points of time, I take
sir,
values. Hello.
sir, can you again explain sampling definition? Sir, just one time.
Yeah, sure, no issues. So see, sampling is nothing but taking some information values at some discrete points of interval of time. Got it?
Yes,
So
sir.
here
Thank you.
in hello,
Thank you,
am I
sir.
clear now?
Yes, sir.
Yeah. So here the blue boxes, what you see is the sampling values we have taken from equal intervals of time. So from the blue boxes, I have drew some the other signal, second signal. What I have imagined, that is the signal what I have received. So if you observe the initial signal to the final signal, there is a lot of difference, right? So the initial signal is completely different from the second signal what I have made. So this is what happens in aliasing. So when you follow the Nyquist sampling theorem, this error is avoided. So that's why it is important to follow Nyquist sampling theorem when we are doing sampling. So this is about sampling. Now we'll come into quantization. Quantization is something similar to sampling itself, but in sampling we take continuous signal, time signal, and break it into discrete time signal. In quantization, what we do is we cut down we continuous amplitude signal is made in discrete amplitude signal. You will understand clearly with this graph. This is graph. So here what you say is we have continuous amplitude signal. So the red signal is the continuous one, and that blue signal what we make is the quantized signal. So what we have done is we have discreted the amplitude into some values over the graph to make discrete signal. So the more number of values you have, the more accurate the quantized signal will be. So this is about quantization. Now we'll get into systems. So system is like it's like you have a signal, it takes some input as a signal, it gives an other signal as an output. So what happens in the signal, a system is it amplifies the signal, or it cut downs, a lot of stuff happens in the system. So mathematically you can represent this system T as an operator of a function, as an operator function. Like if you take an input x of t and a y of t as an output, we can write t of x of t is y of t. So if you want to square this input signal, what you can write it as t of x of t is equals to y of t, that is equals to square times the x of t. So some examples of system is you have a system in signal input, we have a signal output. So what happens in the system, like there are different systems like amplifier. So in amplifier what happens is the amplitude is increased n times, whatever you want to double the amplitude, triple, you can do it. So this amplifier does these things. And if you observe here in this graph, this sinusoidal signal is amplified and there is a phase shift too. So this amplifier does even the phase shift by 90 degrees. So this in time scaling, the signal is time scaled. If in the what you have to remember is if you have multiplied this times this signal by n, if the n is greater than 1, the signal will shrink. If the n is if n is less than 1, the signal will be expanded. So you have a signal.
Sir, what is the work of time scaling?
Time scaling, see, there is nothing much like you need going to deeper into time scaling. What it does is we have it just compresses the signal, right? So you have a signal for n period of time. So you just compress the signal a little smaller. It saves you time. In compressing in this time scaling, there is no loss of there is no change in the signal frequency or something like that. Like there is no change in the signal. What happens is the time is reduced. That's it, or increased. So coming to filters, if you have a signal, the signal consists of different frequencies, low frequency, high frequency, and lots of stuff. So using these filters, you can filter out these signals. So there is low pass signal, the filter, where you keep a frequency as a reference. If you pass a signal, frequencies under that reference signal frequency fall, like will be passed through, and the signal, the frequency, in the signal, the frequency above that reference frequency will be blocked. This is low pass signal filter. So the other one is high pass. See, whatever frequency you put as a reference, in the signal, frequencies above that frequency reference you give will be passed, and the others will be blocked. Other one is bandwidth. So you give a bandwidth f1 and f2, frequency 1 and frequency 2. Frequencies under if there is a signal and frequencies under that frequency will only be passed through this filter. The other one is the opposite of it. If you give f1 and f2, frequencies under that in that signal will not be passed through that filter. These are the 4 types of filters we have. So coming to special class of systems, linear systems. This is nothing but something similar to linear equations. See, when you have what happens, you can simply add on equations, right? Linear equations. So this is nothing but similar to that. If you have an input x of t and there is an output of y of t, and there is one more input of x2 of t and other output y2 of t. With respect to system h, you can add like x of t plus b x of x2 of t, and you have that is equals to a times y1 of t equals to plus b times y2 of t. This is linear system. You have time invariant system. So in this system, the signal doesn't depend on the time. So the behavior does not depend on any of the time. This system is known as time invariant system. LTI systems. This is the combination of both linear and time invariant systems. Whatever you see, the most of the systems we use in real world are the LTI systems. We'll be dealing with this later. Now coming into Fourier series and transform. As you know, every periodic signal repeats itself after some specific interval of time or period. The frequency is the number of times the signal repeats itself in a second. Mathematically, 1 by t is the period. So what is frequency domain and versus time domain? Whatever we have seen the signal before, continuous amplitude and continuous time signal is in the time domain. If you see the red color signal, it is continuous amplitude and continuous time signal. So getting information out of it is difficult because it does not have it does not go periodically, it doesn't repeat itself. So getting more information out of it, breaking down, analyzing it is quite difficult. So when you convert this signal into frequency domain, as you see in the right side graph that is in the blue, you see there is some frequency and there is a peak in the frequency, and thus it is repeated twice more. So what happens is different amplitudes is pointed out in the frequency domain. So those 3 peaks refer to the 3 different amplitudes of the time domain signal. So here we can easily analyze different amplitude signals, and we can get more information out of the from the frequency domain signals. So why did we discuss about frequency domain? Is all about Fourier series, because in Fourier series what we are going to do is we are going to change this signal, time domain signals, into frequency domain signals. So I'm not going to do all the history stuff of the Fourier series, why it is developed, because it's already boring. So putting up here. So the idea was every periodic function can be written sum of sine and cosine signals, whose frequencies are multiples of frequencies of a periodical signal. So this Fourier series, if I have to put it in the mathematical way, f of x is represented with some equation, multiples of a naught, an and bn. So if you want to find a naught, and if you need to find out the coefficients of ai and b1, you need to integrate it with f of x, and all the cosine and sine repeats after a period of time. So after a period of time it becomes 0. So you just have a of a naught equals to 1 by pi f of x. So if you need to find a of n, you need to multiply with cosine, and if you need to find b of n, you need to multiply with sine. So you need to find three values, a naught, an and bn, to find f of x in the Fourier series, and you need to follow the left side theorems to get the right answer. So why is it useful? Sometimes we need to know what frequencies components are there in the present in the signal, so to find more information and analyzing of it. So even to put a filter to it and avoid all the noises inside the signal, we need to find what are the frequency components inside the signal. So that is why we need to use this Fourier transform. See, in this Fourier series, now we are putting it, before we have discussed in the mathematical form, now I'm putting the same frequencies, that equation, in the form of signals. So you can see that x of x is represented, is changed with omega. So now x of t is a periodic signal with period of time t. We can write that in the angular frequency omega equals to 2 pi by t. So we have the coefficients, the other three equations. You need to find a naught, an and bn. So don't your mind into this thing, because we have come into a different solution, like using cosine series. Like we find r of n. R of n is like a cos x plus b sin x. We get r cos x plus phi. See, and if you find this rn term, that will solve the complete problem. So here we need to find single term instead of three terms, that a naught, an and bn. So that so instead of finding three terms, we find this one, and this is easy. This is simpler. That's why you need not to worry about this a naught, an and bn stuff. So this cosine series tells us that our signal x of t uses cosine of different phases and frequencies, and we find like the frequency component to describe a single cosine term with a particular frequency n omega. All cosine and sine waveforms have single frequency component inside them, because they are monotone. If you plot that amplitude parts of a component with respect of frequency n omega, we can call it as an amplitude response. If you plot phase phi n with the frequency, it is known as phi response. So now we'll discuss about exponential series. See, in exponential series, cos phi plus j sine theta sum is represented with the exponential of j theta. This cos theta can be represented as e j theta plus e power minus j theta by 2. So if you substitute this cos theta in the above equation, in the above slides, so we can come into conclusion of x of t sigma d of n e power j n omega t. So now if you keenly observe, if you solve this d of n, you go in, this equation is done. You solve it, you get the signal, right? So why do we need to follow exponential series? So this form has only one coefficient, and we can find phase and frequency are combined in a single variable. So this makes us work very easy than the above equations. Now coming to Fourier transform. Fourier transform is more generally a version of Fourier series, and what we do is here we eliminate all the t terms in it. So we make it these are also known as non-periodic signals also. We define this Fourier transform series of a time domain function x of t to be the frequency domain x of f. Suppose we have an x of t is not periodic. What do you think can be done with the frequency component present in it? So note the Fourier series contain only those sinusoidal components whose frequency was a multiple on the base frequency of x of t. For an arbitrary signals, all the components with any real-time frequency can be represented. Hence, we can take the Fourier transform for them. What is it like? What does this transform do? Is like simply converting that signal we have in time domain to completely frequency domain. We don't use time domain anywhere in the frequency, like in the equations. So we are eliminating all the time related thing. These are the few formulas you'll be looking into to compute this Fourier transform thing for analog. And these are some special signals. So just refer to these slides in the future, and these are all the stuff we'll be looking into, and we'll be solving it. There is nothing much to look into and tell you here. So that's it. Pranav, it's your space now.
Hello. Am I audible?
Yes, Pranav, you can go ahead. You're audible.
So until now we learned about Fourier series and Fourier transform. So it is used to convert a signal from time domain to frequency domain. So this is important because the devices used in real life mostly work in the frequency domain. So we can easily filter out things. The calculations that we have to implement can be done comparatively easily in frequency domain. So the next thing we are going to talk about is signal space. Signal space is used to represent a signal mathematically in terms of other signals. So this is important because convert to form some data, we basically require some basic input as default, and using them we convert the final output. So to here to calculate f in vector space, we can write using triangle law that f equal to e plus c x. So similarly in signal space also we can write e equal to f minus cx. So this is done to represent e in terms of f and x. So basically we are trying to write a signal e in terms of f and x. So if we have n x orthogonal signals, we can convert, we can get the coefficient c for all the n components using this formula. Integrate f into x from t1 to t2 divided by xn from t1 to t2. By using this, we get the components of f in x space. The E here represents the error. So basically what we are doing is we are approximating the f in x in terms of x. So E is the error that we get while approximating. In Fourier series also we approximate the signal in terms of cos omega t and sin omega t, that is various frequency components, and if we increase the number of terms in the Fourier series, the function will get more and more accurate. So the sine omega t and cos omega t, they are the base signals. So here, as written first, there are many types of base signals like trigonometric, exponential, Walsh, Bessel. So basically, any signal can be written in terms of these signals. So in Fourier transform, we use exponential signals, and in Fourier series, we use trigonometric signals. Fourier transform is basically a more generalized version of Fourier series. So here, like it's shown how we can write a signal in terms of other signals. So S1 can be written as A11 omega 1 t plus A12 omega 2 t. So basically what S1 represents is these two coefficients A11 comma A12. So the next thing we are going to talk about is source coding. So until now we have talked about signal. Then the next step would be source coding. So basically the data that we have to convert it to bits. So the source coding is a technique that is used to implement this job. Uh, so here there are some assumptions that we assume that in source coding. In source coding, we basically assume that the system generates random symbols. So the random symbols have a probability. So it outputs using this probability. We can write the code for the data. So I will, like for example, suppose S1, S2 and Sn is the set of output symbols. And for Si, the probability is Pi. So like ABC are the signals, output of the signal, and the probability are 1 by 3, 1 by 6 and 1 by 2. We can represent A using 0, 0, B equal to 0, 1 and C equal to 1, 0 in bits. This is called a code word. Code word is basically the binary representation of a data. So, so the average length of the code can be calculated using Pi into Li. Li is the length of each code word, and Pi is the probability of that code word to occur. So we have to basically minimize this to get the most efficient representation of the data. So in the previous example, as we saw, A, B, C have the probabilities of 1 by 3, 1 by 6 and 1 by 2, and each is of length 2. So the average length is basically 2. So let us take another coding scheme. A equal to 1, B equal to 1, 0, C equal to 0. In this case, the average length is 7 by 6, which is less than 2. So this is a more efficient coding scheme, as we can represent the same data using less number of bits. So there are some things we need to keep in mind while assigning bits to data. So like non-singular codes, the code word for each symbol should be different. Uniquely decodable code. So if we make a signal using code words, it should be uniquely decodable. For example, if we write 0011, it has, in case of a equal to 0, b equal to 1, c equal to 0, 1, it has two possible ways we can represent it. It can be also, as it can be written as ACB or AABB. So this representation is not uniquely decodable. Next thing is instantaneous code. So instantaneous code basically means is that if we start considering bits from any point of time, so we will be able to uniquely decode that data. Uh, that is, we don't require the whole sequence to start decoding. Next is prefix code. Uh, so so it basically means is that uh, no code word should be a prefix that is come before in any code word. Example, if we write a equal to 0, b equal to 0, 1, c equal to 1, so b can also be written as ab. So a is basically comes in front of b. So what can happen is if we are sending the signal and we get 0, so we might decode it as a. So that's why prefix code should not be there. So here are some signals, uh, uh, some code words, and basically we have told like if they are non-singular, uniquely decodable, or and instantaneous. So in the first case, if a is 0, b is 1, c equal to 0, 0, and d is 0, 1. So it is non-singular, it is not uniquely decodable. As if we write, for example, 0, 0, it can be C also, or it can be A. It is not instantaneous, as if we start decoding from any point of time, we will not be able to uniquely decode that signal. Non these all examples are non-singular because each code word has a different representation in binary form. So as you can see, the method for writing a code word for anything seems to be random until now. So we need an organized way to calculate the code word for the data. So so here comes Huffman coding. Huffman coding is basically the most efficient coding scheme, uh, and it is used to calculate the uh, binary form of data. So there are few basic things that we need to keep in mind, that the signals, the code words are arranged from in the order of the probabilities from highest to lowest. That is, and then we add the two lowest probabilities and reorder probabilities and break ties in any way you want. So I will explain this procedure in the next slide. So basically, if we have A, B, A, C, D, and we assign bits to it, first, yeah, before going to the example, I will. There are some features about Huffman coding. Huffman coding is uniquely decodable, and it is not unique. So every time you implement the code, so it will be same for the if the probabilities and the number of bits that you use, if the probabilities of the code were the same, the its representation would be same. So if we have the probabilities, we can uh, get the uh, bits, and if we have the bits, we can get the probabilities. So here is the example. So we have five symbols. Each has a probability of 0 0.4, 0 0.2, 0 0.2, 0 0.1, 0 0.1. So we have to convert this to Huffman code. That is, so basically first we arrange all the symbols in the order of the probabilities, starting from maximum to minimum. Then we in the stage 1 we combine the two lowest probabilities and then arrange them. So in arranging them, what we have to do is the most recent change that we have done, it should be in the top. Like if we add probabilities for S3 and S4, we get a value of 0 0.2. So 0 0.2 should be above S2 and S3, which also have a probability of 0 0.2. Then we do this procedure again, that is add the two lowest probabilities, and again it comes on the top of S1. Then again we add the two lowest probabilities, and it comes top of 0 0.4. So basically what we are trying to do is uh, we arrange all the symbols in the order of the probabilities, add the two lowest probabilities, and arrange the probabilities in their order, uh, again in the order, and we repeat this procedure until we get 1. From 1 we start to assign a binary code to each data. So first we give 0 1, then here we added 0 0.4 and 0 0.2, there also we assign 0 1, 0 0.2 and 0 0.2 we assign 0 1, and 0 0.1 and 0 0.1 we assign 0 1. So here we can change the location of 1 and 0. So basically this is what I was talking about. The Huffman coding is not uniquely decodable. So if we have the code for same probabilities, we can have multiple codes. As the location of 0 1 can be interchanged. Uh, so to write the probabilities of each symbol, we basically have to uh, start from here and go down. So so here S0, uh, here from S0 if we start and follow the arrows, we can see that it is assigned a value of 0 0. And if we follow the arrows of S1, it is assigned the value of 0 1 1 0. So this is basically a tree method. We can see that it forms a tree, and we have assigned values to all the symbols. Uh, for S2, if we go here, we can see it is assigned the value of 1 0 1 1, yeah, 1 1. So we have to go from the top to the bottom of the tree until we reach the symbol S3. So this is so if we calculate its length, mean length, it would be the most efficient that we can get. There are other examples of coding schemes. For example, LZW. LZW is Lempel zip coding scheme. It is very popular and it is used in making a zip. So basically, you might have heard about zip compression tools. So they basically use this coding scheme to compress and form a zip file. Uh, so what it does is it sees the probabilities of a signal occurring and based on that it assigns symbol to data, and using this technique we get the most efficient representation of the data, where the uh, signals symbols which are frequently occurring get a low bit value, and the symbols which occur less get a high bit value. So basically source coding is the process of assigning codes to symbol output by the source. So example, the letter of the alphabet of a text sent are to be converted to a bit format that we so we use compression algorithms to convert the data into the most efficient form. So let's move on to the next part. It's hands-on. So if you have any doubts till now, feel free to ask. So moving on, today we will implement analog signal and digital signal in MATLAB. I have uploaded the files in the file section. In files in hands-on workshop 2. So from here you can download the files for Octave .m files, and for MATLAB you have to download .mlx files. First of all, going to the directory where the files are present. I will be showing you the implementation both in MATLAB and Octave. So you can use both the tools. So first of all, we will So as in the first workshop, we told that the analog signals can't be implemented as analog signals require infinite amount of memory, as it depends on us on how accurate we want to get. So what we basically do is we use timestamps. So we take a lot of values in time, and we use those values to basically approximately imagine an analog signal. So like we use dt equal to 0.01, and using this we make a vector of t. which ranges from -5 to -5 minus dt. So here, as you can see, all the values, we get a vector. So then we calculate sine to pi ft. So this will give us the signal in x. So if we write plot t comma x, you can see that the value has a frequency of 1 hertz, and it ranges from -5 to +5. So similarly, we can write a cosine wave. So cosine x equal to cos 2 star 2 pi ft. So plotting it, we can see we get a cosine wave. The next signal is unit. Unit function is basically it gets a value 1 if the value if the input is greater than 0, and if it gets a value 0 if the input is less than 0. So we can simply write it as u equal to t greater than equal to 0. So it will basically assign value to each number in u in t and return the result to u. So plotting it, we can see the values. This is basically not that clear, so we use a function stem. What stem does is it darkens the value starting from 0. So it basically makes all the things below the current value dark so that we can easily visualize the data. The next function is ramp. So you might know ramp is it is basically 0 if if uh, if input is less than 0, otherwise it is xt. Basically the input multiplied by a constant. So here we use the so here, as you can see, the ramp function, it is 0 for input less than 0, and it is, so the input is t is the independent variable, it is multiplied with u, uh, and we get the output. U is the unit function. So uh, basically the constant that we are using here is 1, and u is used to make all the values below 0 equal to 0. Dot star, as I told in the last workshop, it is used to do element wise multiplication. The next function is delta. So what delta is, it gets a sudden rise in its value at 0. So the condition for a function to be delta is if we integrate the function from minus infinity to plus infinity, the area should be 1. Also, but basically what happens is we want that the value should be very high on 0, otherwise it's 0 everywhere. So its value is very high at input equal to 0. So in discrete, if we have to show this, what we do is if the input is 0, we give the output as 1, otherwise the output is 0. Then next is square wave. So this can be implemented using this. It's basically we can use sine 2 pi ft it is the frequency, then we use the signum function. So what signum does is it assigns the value 1 if the input is greater than 1, greater than 0, and assigns the value -1 if the input is negative. So here we can see the square wave. So here, as if we do stem, then we are able to better visualize what is happening. So this is basically a few signals that we have implemented. The next is digital.mlx. So what happens is if we have input data 0, 1, 1, 0, 1, 0, 0, 0, 1. So we can't simply transmit this data. So what we do is like sampling period as told. So we basically repeat this data again and again to create a wave. So mathematically is what we do is we create a lot of time stamps first of all in between 0, dt is approximately 0 to ta star till ta into m. Basically what we want to do is we pulse duration is 0.1, ta is pulse duration, so we want to repeat each signal for the time as told in pulse duration. So we calculate timestamps according to that only. So by doing s equal to m seal t by a. So what we are trying to do is we do t by ta. So this will return a vector whose value will range from 1 to 1 to 10. So what this will do is we are trying to map this in m. So m seal t by a will return these continuous values as we can see here. So we had an input that was discrete and we converted it to a continuous signal. Then again, while reconstructing the signal, what we do is we take samples at times, sampling times. So we take samples at this time and we get the M reconstructed again by doing sampling time by dt. So this will similarly take the values from this will also take the values from the. So what we transmit, we have the input data m, then we transmit it in channel s, then we have to convert the signal s to m. So basically we are decoding the signal. So here we again calculate the sampling times, and on those sampling times we calculate m reconstructed. So what it does is it takes values of the signal at certain times so that we can reconstruct the signal. So this is basically how we implement a whole procedure of decoding, coding and decoding in MATLAB. The same code can be implemented in Octave also. So first we will open a directory here on the top. Then if I write in the command window signals, so what it will do is it will implement the .m file present in the current workspace. So all the diagrams that we got in the MATLAB, so they all are shown here also. So there are a few changes that you have to do while using Octave. So let me show them to you. What this plot function does, it basically plots the data to figure. So if you don't write figure and you plot all the things, so the latest after the execution of the code, the latest plot will be only shown. But we want to show all the plots, so we plot the data on different figure. So here I write figure 1. Before plot I have written figure 2, and so on. This is to ensure that the data is plotted on different figures. There is one command, hold on. What it does is it waits uh, before plotting the figure. It waits for other plots to be done. So if I have to if I have to show both the plots in a single figure only, so I will do hold on plot, then the second plot, then hold off. So in the figure 1, you can see both the sine and cos waves have been shown in the single figure only. Similarly, for digital, if you want to implement it, write digital in the command window, and it will show all the plots. Uh, Here also, like you can see, there was one thing like you might want to implement Fourier transform in MATLAB. So what you can do is search in the documentation for Fourier. So basically you will get suggestions how you can implement it. So there are FFT Fourier transform. So let's go for FFT. So what it will do is take the input signal X and return us the Fourier transformation of it. FFT is basically an optimized way of calculating Fourier transform. Currently in all the communication systems, FFT is used because it is faster and takes less computation. Here you can, in the documentation, you will see examples also, like this is a random signal, and if we do FFT on it, so what here, like after FFT we get the F, and if we have plot that frequency and amplitude, we can see that it is very noisy. So noisy and the value is approximately ranging between 0 and 0.2. So this means that the signal is random, as all the frequencies have same values. Here in the second example, they have tried. So let me show you third. So this is Gaussian pulse. It is very popular. So if we write the Gaussian pulse and then calculate its FFT, we can see that in frequency 0 it is very high, and as we increase the frequency, the value gets very low. So this is very good signal if we want to transmit the data where frequency is very important. So like we can see that it takes a value of frequency between 0 and 5 only. So this is very useful, like in telecommunication. For example, the bandwidth is limited, so we have to distribute the bandwidth between everyone. So these type of pulses which have a low frequency are very useful for transmitting the data. Similarly, in the next example, you can see cosine wave. So if we there are 3 examples of cosine waves, and if we calculate its FFT, we can see that there is only one peak. So what this peak shows is the frequency of it. So in the starting 2 pi ft, we can see the values are 50, 150 and 300. And in the frequency domain also we can see there is a peak at 50, 150 and 300. So this is basically what frequency domain representation does. So these MATLAB documentation, or you can, if you have, if you want to try any function, you will most probably find it in the MATLAB documentation, or you can simply Google it, like how to implement this function in MATLAB. So that's all for this workshop. If you have any doubts, you can ask now.
No, भैया,